Welcome back to 8.7.01. In this chapter, we will talk about neutrinos and we'll start the discussion with a relatively simple introduction. How does the neutrino look in the standard model and how does it interact? We have discussed the neutrino already quite a bit, so this is more or less a summary. In the standard model, the neutrino is massless. It's a massless particle and interacts via the weak interaction. So it interacts with W bosons and with Z bosons. And specifically, it does not interact with photons or gluons. If you look at the Lagrangian or try to write down the current, we find that there is a charged current via the W, and there's a neutral current via the Z boson. It's quite interesting to think about those two currents a little bit more. So in case of a charged current, if you, for example, have an incoming neutrino, we can determine the flavor, the kind of neutrino we have, via detecting the flavor of the lepton. So if you, for example, identify an electron in this interaction, then the initial neutrino was an electroneutrino. While for the neutral current, when we have some sort of interaction happening, we cannot identify directly the neutrino. Hence, we cannot find the flavor of the neutrino. We can just measure the sum of all flavors of neutrinos in the neutral current. On that story, neutrinos have three flavors. They come in electron flavor, muon flavor, or tau flavor. Neutrinos are left-handed, antineutrinos are right-handed. So that's the story. That's how neutrinos are characterized in the standard model. In the standard model, we can, in the framework we set up, we can calculate cross-sections, scattering cross-sections. And here we are looking at neutrino nuclei scattering. Again, we can split this up in the charged current and neutral current discussion, but they go very much in parallel. So we have elastic scattering, or in the case of the charged current, we talk about quasi-elastic scattering, where we have an incoming neutrino, let's say a muon neutrino, hitting a neutron, producing a muon and a proton. It's called quasi-elastic because we do not break up the target, but we change its kind. So we change from a neutron to a proton in this case. While for the elastic scattering, the neutron just stays intact. We can also have nuclear resonant production, where we hit the nuclei, and then inside the nuclei, we produce a meson, like a neutral or charged pion. And also that's possible in the neutral current exchange. And then we have deep inelastic scattering, where we hit a nuclei or nucleon that hard that will start breaking it up. And in this case, we scatter off the quark and we produce a new quark in the charged current interaction and the same quark in the neutral current interaction. So this is not different from the stories we had before. The intriguing part about studying neutrino scattering is that we do know that we have weak interactions being the dominant being the process, while if we use photons to interact, or we have electrons being interact, then we can have a mixture of weak and electromagnetic interaction. Another important takeaway from this slide is that when we calculate cross-section, we find there's a linear increase in the cross-section as a function of the energy. So while cross-sections for neutrino are small, at higher energies, those cross-sections scale linearly. As we can discuss this for neutrino scattering with nuclei and nucleons, we can also look at neutrino scattering with electrons directly. There's a lot of electrons in the matter around us, and when neutrinos travel through this matter, they can interact with electrons too, and they can leave in the charged current interaction a muon and an electron neutrino, and in the neutral current interaction an electron and the muon neutrino. Also here you see cross-section, total cross-section scale with S with the energy. Good. That's the first introduction to neutrino physics. We'll go into more detail in the following presentations.